In the last module, we started with the frequency domain approach in time series analysis. We saw that the major tool used in the frequency domain approach is the spectral density function or the spectrum. We defined what the spectral density function is, and then we saw a relationship between the spectral density function and the autocovariance function. This relationship actually allows us to move from one domain to the other. So, if we are analyzing in the time domain, we look at the autocorrelation functions, and we can shift to the frequency domain by using the Fourier transform to get from the autocovariance function to the spectral density function, and vice versa. That is, we can start with the frequency domain approach looking at the spectrum and then shift to the time domain approach looking at the autocovariance function and using the relationship between the autocovariance function and the spectral density function. What we will do today is to look at the standard processes that we had been looking at in the time domain. We will be looking at them in the context of the spectral density function. To look at the spectral density functions of some of the standard processes, first just recall that the SEF can be expressed in terms of the spectral density as gamma h is equal to minus pi to pi f omega cos omega h d omega, and this we can define for all h equal to 0, 1, 2, etc. And on the other hand, the spectral density for omega belonging to 0 to pi can be written as f omega equal to 1 by pi gamma naught plus twice summation h equal to 1 to infinity gamma h into cos omega h. Notice that we are restricting ourselves to the range 0 to pi. Of course, this can very easily be extended to the range minus pi to pi, but we will just be keeping ourselves the positive values of omega only. So, we have a dual relationship here. The first one giving us the gamma h in terms of f, and the second giving us f in terms of gamma. Now, let us start with the MAQ process. The moving average process of order q is given by x t is equal to beta naught epsilon t etc. up to beta q epsilon t minus q. Very often beta naught is equal to 1, and of course, we are taking epsilon t to be white noise with 0 mean and variance sigma square. We have seen that in that case rho h turns out to be 0 if h is greater than q. This is because once h exceeds q, and since we have just the innovations on the right hand side, there would be no common innovation between x t and x t plus h, and hence the covariance would come out to be 0. And then we have 1 as rho h if h is equal to 0, this is standard, and for h less than equal to q but greater than 0, we have this ratio of bj plus h summed over j over bj square again summed over j. Now, given this rho h and using the relationship we have got, we can write g omega as 1 by pi 1 plus twice summation over h, and then you substitute the rho h value and that multiply that by cos omega h. So, this is simple, but it is very difficult to look at what is happening here. So, let us look at a simple case of a MA1 process. In a MA1 process, we just have x t is equal to epsilon t plus beta 1 epsilon t minus 1, and in this case the rho h simplifies to 0 beta by 1 plus beta square if h is less than or equal to q, and 1 if h is equal to 0. So, it is 0 if h is greater than 1, it is beta by beta 1 plus beta square if it is between 1. The MA1 model is given by x t is equal to epsilon t plus beta 1 epsilon t minus 1. In this case, rho h turns out to be 0 if h is greater than 1, it is beta by 1 plus beta square if h is equal to 1, and it is 1 if h is equal to 0. And in that case, g omega becomes 1 by pi into 1 plus twice beta cos omega by 1 plus beta square. At omega equal to 0, we have g 0, and you substitute the value of omega in cos omega, and you have 1 plus twice beta by 1 plus beta square in the bracket. If we take omega equal to pi, that is at the other extreme, g pi becomes 1 by pi 1 minus twice beta by 1 plus beta square. So, what does these two results mean, or what does the g omega look like? In the first case, let us take beta equal to 1. If beta is equal to 1, then g omega decreases from g naught equal to 2 by pi to g pi, which is equal to 0. So, it is a decreasing function, and we call it a low frequency spectrum. I will come back and explain why this is so, but generally for beta greater than 0, we have a g curve which is something like this, which is going down, decreasing from 0 to pi. On the other hand, if we have beta is equal to minus 1, then g omega increases from g 0 equal to 0 to g pi equal to twice 2 by pi, and we call it a high frequency spectrum. And in general, for beta greater than 0, we have a g function which is going up between 0 and pi. Now, why is this called low frequency spectrum and high frequency spectrum? This is because, look at the first case, when beta is equal to 1 or when beta is positive. The low frequencies, that is frequencies which are close to 0, they have larger ordinates, and therefore, we say that it is a low frequency spectrum. That is, the underlying curves which primarily make this series are primarily of low frequency, whereas in the second case, most of the frequencies are high towards the right hand side, that is towards pi. So, the ordinates are high in this case towards pi, and therefore, the larger frequencies play a major role in explaining the underlying sequence when beta is equal to minus 1, and hence we call it a high frequency spectrum. Now, let us look at a AR1 process. In a AR1 process, we have x t is equal to alpha x t minus 1 plus epsilon t, and we know that rho h in this case becomes alpha to the power of h, and for stationarity we require that the modulus value of alpha is less than 1. Given this, we can get g omega as 1 by pi into 1 plus twice summation over h alpha to the power of h cos omega h, and this after some simplification will come out as 1 by pi 1 minus alpha square by 1 plus alpha square minus twice alpha cos omega. Again, we have at the lower end at omega equal to 0, we have the g omega value to be 1 by pi into 1 plus alpha by 1 minus alpha, and at the upper end, that is at pi, g pi is 1 by pi into 1 minus alpha by 1 plus alpha. Again, let us look at what this means. For alpha greater than 0, g omega decreases from g naught to g pi, and again we have a low frequency spectrum with the higher values of omega in this case having little contribution, and the lower values having the maximum contribution in the makeup of the process. On the other hand, if alpha is less than 0, then g omega increases from g naught to g pi, and the high values now have a larger role to play in making up the process, and hence we call it a high frequency spectrum. However, for more complex processes, it is not so easy to interpret the spectrum. As we saw even for the MAQ, you have too many parameters. It was easy to derive, but interpretation of that would be difficult. In fact, for the ARMA processing general or for the ARP model, even deriving the spectrum becomes much more difficult by this simple rule. Hence, what we do is we look at a result which relates the autocovariance generating function with the spectral density function, and then look at how we can use that to estimate the spectrum. So, first let us define the autocovariance generating function. It is given by Cz, which is sum over h from minus infinity to infinity gamma h z to the power of h. So that the autocorrelation generating function would automatically come out as Rz, which is sum over rho h z to the power of h, and you can readily see that this would be Cz by the variance of xt. But we will restrict ourselves to the autocovariance function generating function in general in this case. Let us look at a result that we have. Let xt be a linear process. So, xt can be written in terms of UTs as xt equal to summation j equal to 0 to infinity aj ut minus j, where UTs are white noise with 0 mean and variance sigma square, and these are absolutely summable coefficients. So, the AJs are absolutely convergent, so that it really means that summation of modulus of AJ is less than infinity. So, under these conditions, what we can say is that for hz defined as aj into z to the power of j summed over j, cxz would be hz into hz to the power of minus 1 into cu of z. So, we know the function hz, and if we know the autocovariance function or covariance generating function of u, we can get the autocovariance generating function of x. But more importantly, we also have these results where the spectral density function of x can be obtained as h e to the power of I omega into h e to the power of minus I omega into f u omega. So, if we know the spectrum of u, we can use this relationship and get the spectrum of x. So, this is one simple way of getting the spectrum of x, and we can apply this to the AR or the ARMA process, because we can write this as a linear process. We can always express them in terms of an infinite sequence of past white noise. So, in that case, if we can write that as a linear process, we will be able to use this result and get the spectrum of the corresponding more complex process. Let us see how we can do this. We'll start with the ARMA PQ process. So ARMA PQ is given by xt is equal to alpha xt minus 1 to alpha p xt minus p plus epsilon t plus beta 1 epsilon t minus 1 to beta q epsilon t minus q, where the epsilon t's are the innovations or the white noise. Now let us write yt is equal to summation j equal to 0 to q beta j epsilon t minus j. That is primarily the second part. Notice that in this case we are taking beta naught to be equal to 1. Now if we do this, and since the epsilons are innovations or white noises, they have a spectral density of sigma square by pi, and hence we can write Fy omega in terms of the spectral density of epsilon and the h functions, which in this case would be summation over j from 0 to q beta j e to the power of I j omega and beta k e to the power of minus I k omega, again summed over k. So these two terms into the spectral density function of the innovation, that is sigma square by pi, gives us Fy omega. On the other hand, if you substitute yt in the model, that is if you write yt instead of epsilon t plus beta 1 epsilon t minus 1 etc., then you can see that yt is equal to xt minus alpha 1 xt minus 1 to alpha p xt minus p. And let us write this as alpha naught star xt plus alpha 1 star xt minus 1 etc., where alpha j star is minus of alpha j and alpha naught star is equal to 1. Now if we do this, again we use the same result. Again we can express y or its spectrum in terms of the spectrum of x. And if we do that, we get this. So in this case, unlike before, we do not know what the spectrum of x is. So on the right hand side we have fx omega, and on the left hand side we have Fy omega, and these are related by these two quantities, summation j equal to 0 to p alpha j star e to the power of I j omega and summation k equal to 0 to p alpha k star e to the power of minus I k omega. Now if we get this, since we have another expression for Fy omega, we can equate the two, and then what we can do is that for omega belonging to 0 pi, we can get fx omega as sigma square pi into this ratio. This ratio actually, if you equate them, take this coefficient of fx omega from here to the left hand side as a denominator, and you get this. And you can see that this can be easily written as sigma square by pi into mod of psi e to the power of minus I omega whole thing square by phi e to the power of minus I omega absolute square. So what you are looking at basically, what is psi and phi? Remember that phi is the characteristic function of the AR component and psi is the characteristic function of the MA component. So you can write it in terms of the characteristic functions of the two components as a ratio of it, and we can get the spectrum for x which follows the ARMA PQ model, and this would not be very simple to look at, but we can get a expression for this way. Now let us look at a special case where p is equal to 1 and q is equal to 1, and we have the model xt is equal to alpha xt minus 1 plus epsilon t plus beta epsilon t minus 1. So for omega belonging to 0 to pi, this formula reduces to something like this, which on simplification gives us sigma square by pi to 1 plus beta square plus twice beta cos omega by 1 plus alpha square minus twice alpha cos omega. It's again still not readily seen as to how the function looks like, because this would be heavily dependent on what the values of alpha and beta are. This is what we saw for the simple AR1 or the MA1 process, that is, for negative values you get one type of curve and for positive values you get another type of curve. In this case you have two parameters, and the combinations of those actually would lead to different type of curves. But once you have put in those values here in this model, you would know what the function looks like, because it will then become simply a function of omega. So this is how actually we look at the spectrum for a ARMA process. Very quickly, let us have a quick look at the AR process in general. For ARP, we have a model xt is equal to alpha xt minus 1 up to alpha p xt minus p plus epsilon t. It should come out as a special case of the ARMA PQ model with q equal to 0, but let us derive it directly. So, we will write epsilon t in terms of the alpha naught stars, alpha 1 star and alpha p star, where the alpha j stars are defined as before in the ARMA case. And once we do that, in this case we just do it directly. On the left hand side we have epsilon, which is written in terms of the x's. So, we get the spectrum of epsilon, that is f epsilon omega, in terms of the spectrum of x, which is fx omega, and you have these two coefficients which will be your h function. Once you have got this, and since the spectrum of omega is going to be sigma square by pi, so you replace that on the left hand side, and then you can express fx omega as sigma square by pi and the inverse of the coefficients here on the right hand side of the equation, the coefficients of fx omega, and you get this expression. And when you simplify this, you get an expression for the spectrum of a ARP. A special case we will get the spectrum for the AR1, and probably the spectrum for the AR2 is simple, but for higher order AR models the spectrum would not be so simple to look at, but we can get the expressions for it, and once the alphas are known, once they are replaced, it's easier to look at how the function looks like. In today's lecture, we have looked at several examples of time series and saw how you can find the spectral distribution for each of this. For the simpler ones like the MA1 or the AR1, it is easy to derive because we know what the autocovariance function is, and transforming it by the Fourier transform, it is easy to get the spectrum. But in some cases it is not so easy to convert from one to the other, and therefore we got a result relating the autocovariance generating function with the spectral density function, and using that result we could see that we can use the autocovariance function for a ARMA process and convert it into the spectral density function of the process. What we will do in subsequent classes is to estimate the spectral density function.